Today I'm going to talk about some work we do in New Mexico on bank erosion repair, and I wanted to start off with sort of two titles. I'm just sort of telling a joke, but I came up, my friend told me there's a conference in Grand Junction, and this was 3:30 on Friday afternoon, and Kara wanted stuff at 5. So I came up with a name, which is Bank Erosion with Sod Tiles. I can't even remember, it's not that exciting, at the Valles Caldera National Preserve. I visited my friend and colleague, Dr. John Coop in Gunnison, and he said, that's just, you got to make it better. So, second title. A novel stream bank restoration technique for herbaceous riparian systems, integrating experimental approaches with restoration design. Which among us has their PhD? And it would be John. Okay. Next. Let's see, how does this look? I just want to give some credit to the project funders. This is an EPA-funded project as well as State of New Mexico. This is funded through 319 funding. And for a while, New Mexico had a river ecosystem restoration initiative project, which unfortunately kind of died politically. This was funded through both those projects, and it's run through a nonprofit called Los Amigos de Valles Caldera. I work with Bill Zedike, who Gay spoke about earlier, Gay and Claudia talked about, and Van Clother of Stream Dynamics. So there's some of the people involved. The Valles Caldera, just sort of kind of where it is. This is northern New Mexico right there, the Valles Caldera right there. Santa Fe, it's about an hour from Santa Fe, 20 minutes from Los Alamos in the Jemez Mountains. This is a old volcano that blew the top off. It's a huge, one of the largest calderas in the world, I think. And then further eruptions kind of filled it with mountains on the inside, but it was a 27,000-foot mountain a million years ago. This whole area was a Spanish land grant. A lot of northern New Mexico was deeded to different families and went into private hands around the turn of the century. It was a private ranch. I grew up nearby. It was a private ranch until early, I want to say the early 90s, and they would literally arrest you and take you off. So it's been in very strict management. It was bought by the federal government and put in a special kind of management type. I think it's the only one of a national preserve. So you can't just drive there and go in. You have to sort of, you can pay to fish or you can get in somewhere. It's in kind of a unique management place, and it was supposed to pay for itself, and that sort of led to some issues with it. But I'm very privileged to work there. It's a pretty unique place. Basically, here's some of our project sites. We've worked all over. I'm going to show you where this is really uncomfortable. All right, that'll work better. Yeah, I can't really read all these, but this is San Antonio Creek right here. It flows from east to west and south. Meets with the other part of the east fork of the Jemez. The Jemez River flows into the Rio Grande near Bernalillo, just north of Albuquerque. And yeah, that's all right now. Oh yeah, San Antonio Creek. It is impaired for sediment and temperature. And so I'm going to kind of talk about why and what we did to try to figure out how to fix it. This area was very heavily grazed. There's 100,000 sheep in 100,000 acres, so you can do the math right there, for many years. And then kind of after World War II, everything switched over to cattle. They didn't need as much management. It was much better grazed, but a lot of very historic erosion happened, leading to a lot of bank erosion. Now, the general process for bank erosion in a lot of streams is that sort of grazing tramples the edges, widens the stream. Sediment also falls in the stream at the same time. Since the stream's wider, it's shallower, and it can't move that sediment out of the way quite as easily. You can't transport it downstream. That sediment often builds up on the point bars. They push against the outer bank, and you have bank erosion. That kind of picture right there, bank erosion. So streams actually evolved back from this, and we did some research to figure out kind of where we were in this process. And bank erosion can contribute to something like 50 to 90% of your sediment problems. In this particular system, these are big valles, big grassy valleys. It's probably around 90%. It's most of our problem. And temperature is also, these widening of the streams leads to temperature problems from more solar irradiation. Okay. So we started with a walking assessment of 16 miles of creek and identify 130 eroding banks, 70 south facing, 60 north facing. We graded them on severity. And the one thing we saw in this is that the entire watershed had dropped about a bankful elevation. So it's just acres and acres and miles of water storage lost, at least a foot of water table drop. Also affecting the vegetation. So the vegetation changed from, basically huge wide valleys full of wetland plants to kind of, patches of wetland, but with more of a mesic plant community that's less resistant to erosion, which kind of leads to the feedback loop of bank erosion. So we looked at this data and we actually tried to assess and see if we could tie in these severity scores of bank from A to C with the parameters we could measure in sort of a fast walking survey. So we looked at bank height, we looked at bank length, and we looked at rates of curvature. Surprisingly, we found no relationships, and we really thought bank height and radius of curvature would kind of, tie in and show us something, but they didn't. And what we did see, we also wrote down sort of a subjective score on vegetation, and we saw that was really closely tied into bank score. If it was really bad, it was an A. If it was good, it was a C. With vegetation, we don't know if that was sort of the cause of the bank erosion or a result of it. So is it eroding because it doesn't have vegetation, or has it eroded and therefore very little vegetation is left? And a lot of things in streams work that way. They're kind of all tied together. Next, we looked at the aerial photos and digitized the 35 aerials for the entire preserve. This was just a section we worked on. And the light blue, if you see in here, it's braided. It's a little bit straighter. That's the 35 channel. A lot of braided areas. And some of it was pretty indistinct. These are pretty fuzzy. Then we looked at the actual, what we call the belt width, the amplitude of the wavelength, and saw that, yes, it was straighter and braided in the past, and is the amplitude increasing, becoming more sinuous, therefore flatter. So it's probably in a healing trend right now. So it's just sort of some neat stuff to look at. Then we walked the banks, me and my colleague, Dr. Jonathan Koop. He's a professor at Western. He is a wetland plant specialist. So we walked the banks and just kind of, I'm a geomorphologist, he's an ecologist, and we tried to come up with successional pathways so that obviously maybe at one time all these banks were eroding, and we wanted to know how does the river fix itself. And so we came up with two pathways. This is pathway 1, and look at this clump of veg here. And this is very strong wetland plants, probably what we call Northern Territory sedge, Carex utriculata. All you have to know is it's the sedge that grows in the water. So it's, in this pathway, basically, this tall eroding bank moves backward until it sort of widens, kind of to within its potential. Maybe the water table drops a little, the stream's a little low flow. And then in this pathway, this kind of vegetation moves in on that sediment right there, and is strong enough, it's very tough material, as I'll talk about later, that kind of anchors it. And while that top bank can continue to erode back, this bank is very strong. So that's one pathway. The second pathway is kind of down here. I'm probably standing in the way. But in this sense, maybe there's no sedges nearby, but the river widens enough it actually kind of creates a bar in the stream. Again, in a low flow period, which we've had a lot of lately. This gets colonized by what we call spike rush, which is, this is Eleochus palustris, but it's an early successional wetland plant. And over time, maybe these carices, these large sedges from this bank kind of hop over, propagules slowly move over, and that gets established. So what we did with that is created two techniques. Now, we wanted to work with, kind of had a large design discussion on what we wanted to do here. We didn't want to bring in outside materials. We could build cross veins, we could bring in rocks, we could bring in logs, we could do different things. And we wanted to see if we could work with materials on site, and mainly because we wanted to do large-scale work and we wanted to have low cost. So our techniques were to use vegetation on site. And we kind of had two choices. The top technique we call the bank technique. We made sure this vegetation had some wetland vegetation in it, some sort of mesic species. And we took that material, and then down here, we carefully lifted off 3 by 3 foot chunks and kind of placed them in the stream, knuckled them down with the excavator, and worked our way down. And this took about half a day right there. The other treatment we tried was, what if we took the end of the point bar, which we kind of feel was probably, due to the high level of sediment, might have been a little bit too extended anyways, and we took off the point bar side and laid it as a bank full bench. And so these are two techniques. We had controls. We took before and after data and set up a little experiment. This is the monitoring technique we used. We came up with this. We call this a bank section transect. This is parallel to the bank, about 10 feet on either side or on the bank, and then it runs through sort of that eroding bank section. And we do line point intercept at every foot down this transect, and we take a measurement from the middle of the transect to each sort of the edge of vegetation to the inner berm on each side of the bank. And so this is our data, so we wanted some real concrete data from this so we could measure it. So here's how they turned out. This is sort of the bank sod treatment before it was done, and after 1 year later. It really does look that good. Came in very nicely. We actually had a fire in the watershed, Las Conchas fire, so about 40% of this watershed burned. And so the summer between these, we had 6 or 8 big floods, which kind of we don't have really in New Mexico, not in the summertime, not from monsoons. So we had a lot of flooding events that held out against that. The point bar treatment looked pretty good too. Here it is, kind of coming in very nicely. That's a year later. So it held very nicely, didn't wash out by floods. We have not had good snowpack that tested against a long-term snowmelt event. Next, here's some data from this. We actually, we did a little experiment. So we have the point bar is green, the bank is red, and the control is black. And interesting thing here is we saw that the bank treatment, because that sod was already developed, right 1 month after installation, it was pretty high cover, 50% vegetation cover, but it didn't get any better. Whereas the point bar treatment, moving those big sedges, they kind of fall apart, surprisingly. So there's a lot of dirt, but we see this kind of slope, and we think it's just going to continue to get thicker as we go. So that kind of showed us that we like that point bar treatment. Both treatments reduce the width of the channel, which actually we want in this situation. We want a channel with a stream power to move sediment through here and move it downstream and put it on the riffle. So we like that. That was significant. And then we also take a measurement to the closest bank, and basically this is how we put up our monitoring, but it started out, the bank is on 2 feet on one side, right there, 2 feet on one side of the tape, went to 2 feet on the other side, and it didn't move. So we didn't see a lot of erosion of these banks. Our recommendations from this is that we fill the point bar sod, this is right here, consisting of these 2 species, water sedge and Northern Territory sedge. So superior treatment as it kept improving over time. We felt the bench treatment was slow in establishing, even though it had wetland plants. We've learned some things about what species you use. This is a very soggy spot, and our plants were not able to really, they didn't really spread very quickly. So our bench treatment, as if we'd taken this material right here and put it there, didn't work so well, but it still helped. And we also learned something about grazing. We have about 5,000 elk on the preserve. For some reason, they put out 60 permits a year. But elk are everywhere. And so having a wider bench and having sort of not this chunky sod, but actually sort of a gooey sod, if that's a scientific thing to say, basically it can get grazed. And a lot of animals come down here to drink from the river. So this was a treatment that could, it's been trampled some places. It grows back just fine. This treatment needed no external materials, only an excavator and operator, about a half day for 150 or 50 feet of bank. So it's very fast, and it matches materials to the system. Another thing I didn't mention is when we made our choices, we're only fixing banks eroding in the first or second terrace. Frankly, banks don't really erode when they're at bank full height, but we were pretty careful to choose which ones we used. Some of these places we want erosion to occur. We don't want to stop stream channel sort of evolution, but we were pretty selective on that. We got so excited about sod, I'll tell you a little bit else about it. This is a different treatment. This is called a plug and pond treatment. It's a gully through a wetland right here. This is about 3 feet deep. And we said, I wonder if we can save sod to do our plug and pond. So we came in and we took a little track loader and we stripped all the sod off of this whole area and then literally laid it out. And this is the true sod tile technique. That's about 6 by 3 by 1, and laid it out in lines. And then stockpiled topsoil, grabbed the clay and built a clay core dam with the loader laying it in courses, and then put the sod back on top. And literally, sod is amazing. The bluebells were still waving in the wind. It didn't get hurt. Didn't even rain much that summer, but it really held very nicely. So, but we learned something about that. We really thought that we'd use the same type of really thick wetland sod. You actually have to match the sod to the kind of the geomorphic position that exists. You want to use, for this particular project, we ended up using Juncus balticus, Baltic rush, Arctic rush, and then sort of a Kentucky bluegrass sod. If it held together, it worked well. The real wetland plants just kind of died off because they weren't wet enough on top of the dam. So we learned about that. So thank you for your time, and I'll take any questions you have. Thank you, Gay. This is about 8,500 to 9,000 feet in New Mexico. So it's here it'd be probably 8,000 equivalent to.
Thank you, Steve. Those are great images.
Thank you very much.
Our